SwayamPrabha. Digital India. Educated India.
Hello and welcome to the second session of discussion on machining science. So, let me remind you, in the first session we defined machining as one of the manufacturing processes in which the desired shape, size, finish and accuracy is obtained by removing the excess material from the workpiece in terms of small chips. And the different surfaces that we get, it is because of the relative movement between the tool and the workpiece. We have seen the different kind of relative movements, because of which we can get a flat surface, we can get a cylindrical surface, either it is an external or it is an internal or it is a tapered surface and so on. Then we said that the basic mechanism which is responsible for material removal is the plastic deformation. And before the metal gets segregated, so that we can get the desired shape, size, etc., the material has to go through the elastic deformation, plastic deformation, then the strain hardening, and then it gets fractured. So, we said in the elastic, this is the elastic limit, this is the tensile test of a mild steel bar, and here the material gets fractured ultimately. Of course, this is shown in an example of a mild steel material, and for as you understand that for brittle material it is not like that, because brittle material does not go beyond this point, okay. It breaks because the material is brittle and it cannot withstand the high strain rate. So, we get the discontinuous chips. Now, for the mild steel or for any ductile material, what we get is the elastic limit, and then it becomes plastic, and then the strain hardening, and then it gets fractured. So, the chip is segregated from the workpiece, we are getting the different kind of surfaces. Then what we said is that this is the region where the material gets strain hardened, and the strain hardened is actually defined by the material being able to withstand the increased load despite the uniform reduction in cross sectional area. This is called the strain hardening, or sometimes it is also called the work hardening. After that, we said this necking occurs somewhere here, because the extension becomes large, the strain hardening is unable to cope with the decrease in the cross sectional area. So, when the necking is formed, the deformation becomes locally, okay, and then it gets unstable and it gets fractured at any time between the E and the F. Okay. So, this we have discussed in the first session. Now, let us discuss the stress and strain in brief, okay, because we understand that material removal is basically because of the plastic deformation and high strain rate of deformation. Okay. So, the mode of deformation of material under applied load will depend not only on the magnitude of forces and the mechanical properties of the material, but also on the way in which the forces are applied and they are combined. Now, nominal stress, for example, that is defined as the load divided by the original cross sectional area of the bar, this we all know, and the engineering strain is defined as the extension per unit original length. Now, therefore, the load extension diagram of a bar with unit cross sectional area and unit gauge length is therefore the nominal stress strain curve for the material. What I mean to say is that if we have defined that the nominal stress is the load divided by the original cross sectional area of the bar, and the engineering strain is defined as the extension per unit original length. In that case, this is the load extension curve. This can be said to be as stress here and the strain here, okay, stress strain curve. So, this is normally you can see from the book that these kind of curves are given as the stress strain curve. All right. the stress when considered as acting perpendicular to a surface, this is called the normal or the direct stress, and when parallel to a surface they are called the shear stresses. This we all also know. At any point in a stressed body, the stresses may be resolved into 9 components acting on the face of an imaginary cube. Let us say we have an imaginary cube, let us say like this, all right, and this is in a system of axis, for example like this. Let us say this is 1, this is axis number 2, this is axis number 3, all right, and this is a stressed body. So, here the stresses may be resolved into, as I said, 9 components. Now, the stresses which are acting, as we said, perpendicular, they are the normal stresses or direct stresses, let us say 3 3. This is the axis, so the stress acting normal, this is 1, let us say, and this is the 2 2 1 1, and this is. Now, here the stresses which are acting parallel, for example, in this case like this, and here these are the 2. So, this we are calling as shear stress, this is 3 1 coming from 3 to 1, and this is the tau 3 to 2, all right. And here also we will have 2, that is, this is the tau 2 1, and here will be parallel to the body, parallel to the surface, this is the tau 2 3, and here also we will have the 1 here in this direction and 1 in this direction, well in this direction. So, as you understand that this will be the tau 1 3 and this will be the tau 1 2. So, if you see that there are 9 components of stresses which are there, and the axis defining the faces, like for example, here we have taken 1, 2 and 3 of the cube may be chosen in any direction, and for some purpose it is convenient to choose axis so that the shear stresses are 0. In that case, the normal stresses acting, they are called as the, as you know, they are principal stresses, all right. Now, the Morse circle stress circle construction is a convenient means of relating these stresses on any plane to the principal stress. So, in that case what happens is that you have the circle. So, this is the Morse circle, and the center of this will be lying on the let us say it is here, this is the direct stress, this is the shear stress, all right. And in case of 3D, when we have the 3 dimensional, then let us say principal stresses are 1, then let us say this is okay, sigma 2 and this is 3. So, this is the 3 diagram normal. Okay. And if we have the 2 dimensional cases, in that case this will be shear stress and this is the normal stress, and then we have the Morse circle and we have this sigma 1 and this is 3, all right. So, here any point on the surface will be defined by a point on the circle, on the Morse circle. So, this is let us say B point, okay, and here it will be inside this. So, this is the point B, and this will define the sigma B, and this will be defined as the B. Okay. So, this is the point which will be on the Morse circle, and this is defining the stress on of a surface, and this is the 2 dimensional, this is the 3 dimensional case. Okay. Now, suppose the L1 is the original length of a bar, and small l is the current gauge length after the elongation. So, L1 L0 is being elongated to let us say small l. Then the true or natural strain, which is defined let us say by E, is defined in terms of the strain increment, that is E will be integral of dl by L integration from L0 to L. Mind it, L0 is the original length of the bar and L is the length after it is elongated. And if you do the dl by L from L0 to L integrated, this will be logarithm of L by L0. Now, the advantage in using the logarithmic definition of strain is that the logarithmic strains are additive in sequential process, all right, which is not true for the linear strains. Well, what does it mean additive in sequential process? Let me give you an example. Suppose a bar is strained during a tensile test from L0 to L1, all right. The true strain as it is done here in this case will be, let us say, E prime. This is logarithm of log of L1 by L0, all right. And this bar from L1, it has gone further being elongated to, let us say, L2. The further strain will be, in that case, will be E2 prime, and this will be log of L2 by L1. So, therefore, the total strain that is coming out to be E prime plus E2 prime, and this is log of L1 by L0 plus log of L2 by L1, and look here, what we are getting is that log of L2 by L0, all right. So, that is why we are saying that this is additive in nature, all right. They are being added up, and what we are getting is that whatever in between elongation that has been taken, so and that has been performed. So, we are getting we will be interested in the final version of the length after being elongated and the initial version of the initial length. So, if we take the logarithm and divide the final length after being elongated by the original length, we will get the final strain or total strain that is happening. So, this is not true in the linear strain. When the linear strain happens, they are not actually additive in nature, all right. So, this is the advantage. Now, let us discuss the mechanism of plastic deformation, all right. Now, this mechanism let us try to define or describe in terms of in the atomic scale. For example, if we have the lattice structure like this as it is shown here. So, by lattice structure you understand that this is the these are the atoms which are in equilibrium position located in the material. So, this is called the lattice structure, and for plastic deformation to occur, it is necessary to have large scale slipping. I will explain it to you what is slipping, how it happens, where two planes of atoms slip past each other, causing one entire section to move relative to another. Now, when we have the lattice structure where the atoms are in equilibrium position, all right, here if we are applying some strain for stress, for example, or shear force, for example, in that case one full layer of atoms, it is moving with respect to another layer, and if the forces are high enough, in that case these layers after being slipped or after being moved, they will remain in position. So, that we are calling as a permanent movement or plastic deformation in one word. Slip. So, we are saying that to have large scale slipping, this slip means that the movement of one layer with respect to another layer, all right. Now, the slip occurs more easily on certain crystallographic planes depending on the crystal structure, meaning that where now when you are applying the shear force or shear stress, okay, the atoms are moving. Now, how to find out that which layer will be moving with respect to which layer? So, those are called the slip planes, and the slip planes they depend on the materials, all right. So, these are the slip occurs at the slip planes, and crystallographic planes that are farthest apart are also the ones of the greatest atomic density. Now, what we are saying is that when two layers of atom have to move with respect to each other when the shear force or shear stress has been applied, then it will move along the slip plane which are the farthest apart from each other, all right. Meaning the two layers, they are farthest apart from each other, and those two layers will have the maximum atomic density. Okay. So, I will give you an example. Suppose we have a material where we have the face centered cube, which is a face centered cube. You are all familiar with the face centered cube. There are BCC, there are FCC. Okay. So, let us take an example of the FCC. Here we have atoms like this at each face. All right. Now, if you see the face centered cube like this, you can actually draw a plane like this. This is the plane in which, along which you will find the maximum atomic density. The number of atoms will be maximum. You cannot draw any other plane where these many atoms will be located. So, that is why we are calling as the maximum atomic density. Now, if the two layers will have the maximum atomic density, then in between the resistance to the plastic deformation will be less, minimum. So, therefore, material will be deformed along this plane because it will get less or the minimum resistance to the plastic deformation. Because these two layers are farthest apart, and farthest apart because these two layers have the maximum atomic density. And why maximum atomic density, how it happens, I have shown it to you in this example of the FCC, face centered cube. All right. Now, the mechanism of plastic deformation to continue, let us see how this slip occurs. Now, when two atoms are sufficiently close to each other, the outer electrons are shared by both the nuclei. All right. What I mean to say is that suppose there are two atoms here and they are sufficiently close, let us. So, here is the nuclei, here is the nuclei of another atom, and here are the electrons which are outer electrons of both of them. Okay. So, this outer electron belongs to this atom, also belongs to this atom. Now, once they are very close to each other, these outer electrons, they will be shared by both the nuclei. Okay. So, therefore, as a result there will be an attractive force between the two atoms and repulsive force, because when two nuclei will be coming closer, all right, they will have a repulsive force. So, as a result what is happening is that when two atoms are very close to each other, they will be attracting each other because these electrons are shared by both the nuclei, and then when they are coming closer to each other, they will not collapse because these two nuclei will repulse each other. All right. So, this is exactly what happens. This attractive force changes like that in the sense that as the interatomic distance is decreasing, the force is increasing. Okay. As they are coming closer to each other, that attractive force is becoming more. Similarly, this is the curve for the repulsive force, and this also becomes more as the interatomic distance is less, meaning if the two atoms are coming closer to each other, they will have more and more repulsive force as well. All right. So, first thing is they will have the attractive force as well as they will have the repulsive force. At this point where the attractive force curve and the repulsive force curve both are crossing each other, in that case this is the distance which is called the equilibrium distance, meaning at this distance the atoms are in equilibrium position, they will not be collapsed, they will come to an equilibrium position where the attractive force and the repulsive force both are same. All right. So, let us understand this, and then we will talk about we will continue that discussion little later after we discuss these structure. These atoms that we have seen form a polycrystalline solid with atoms in equilibrium position. All right. So, here these are the atoms. All right. Here we can see the polycrystalline, this is the polycrystalline solid, and here we have the grains. Each grain has the atoms which are located in the equilibrium position. All right. Now, these crystals, polycrystalline materials, solid, these are not perfect. That means, in the lattice structure there are always imperfections. Okay. They are not perfect in the sense not all the atoms are arranged in the way that is shown here, may not be arranged in the way that is shown here. So, what are those imperfections? These are the imperfections, they are known as the point defect, line defect and the surface defect. let us take example. The point defect is something like, for example, in a lattice structure there is one atom missing, all right. Here you can see there is no atom. So, this is a defect, this is called a defect or imperfection, and this defect is called the point defect and known as the vacancy, because there is one atom missing in the lattice structure. Similarly, look at this lattice structure, for example, all of a sudden one atom is taking a very odd position in the lattice structure. These are all the regular positions the atoms are taking, but here is the atom which is taking an odd position in the lattice structure, and this defect is called as the interstitial impurity. Next is also a point defect. These are all point defects. Okay. Now, the next defect is the substitutional impurity. Here one atom is a foreign atom, in the sense that this atom does not belong to this lattice structure. Somehow it has taken the replaced one of the atoms in this lattice structure. So, this is called the substitutional impurity, because this foreign atom is substituting one of the atoms in the lattice structure. So, all these are the point defects, and they are actually, these point defects are there in the polycrystalline solid normally. Now, there are, apart from the point defects, there are also line defects. This is called the dislocation. If an imperfection extending along a line has a length much larger than the lattice spacing, this is the lattice spacing, atomic spacing. So, then that is called the line defect, all right. And when an imperfection extend over a surface, so this is called the surface defect, and when the surface defect happens, you understand that this is twinning, also it is called the twinning. That means, the deformed surface is a mirror image of the other surface. So, this is called the surface defect. Okay. Now, let us see the elastic and plastic deformation in the atomic scale. So, if you plot the curve of the net interatomic force versus the interatomic distance, this is the line that we can form, okay, we can get, all right. And this line we have shown that when they are interacting with each other, you remember this attractive force and the repulsive force. So, we are saying that for the net interatomic force versus the interatomic distance, this is the line which can be obtained. And suppose there is a point here which is in the equilibrium position. Okay. This distance is the dc. This is the equilibrium position where the atoms are in the equilibrium stable in the lattice structure. Let us say this is the point where it is in the equilibrium position. It has to be this point, because here this is intersecting the axis, all right. So, this must be the equilibrium position, and suppose from here we are moving the atom from here to here, and if the distance that we have moved dA, it is not more than 5% of the d equilibrium, in that case this will be the elastic deformation. Once again, if dA, this distance after the atom is moved from the equilibrium position here, where the curve is intersecting the axis, all right, this is the equilibrium position. When the atom is moved from this position to this position and the distance becomes dA, if dA lies within 5% of the dE, all right, then upon removal of external forces, the atoms attain their original position, meaning that if it comes to this point and if this is the dA is less than 5% of the dC, in that case after removal of the force, this point goes into this, I mean the atom comes from this position to this position, if the force is removed. What is the force we are talking about? We are talking about the shear force, this is acting, okay, which is causing two planes of atoms to move with respect to one another. And if this force is not more than 5% with respect to the equilibrium position, in that case it is elastic deformation. That means, if the upon removal of the force, the planes are again coming back to the initial position, all atoms are again becoming in the equilibrium position. If dA becomes more than 5% of the dE, this is actually the equilibrium position. So, let us call it dE and not the dC, as I said. Now, if dA becomes more than 5% of dE, then upon removal of external forces, the atoms do not come back to their original position. Okay. And as we understand that this is called the permanent deformation or the plastic deformation, when the two atoms move past each other and they stay in that position. Upon removal of the external force, it will not come back. So, this is the plastic deformation. This is how we can actually understand the elastic or plastic deformation in the atomic scale, when we know that in a lattice structure the layers of atoms, they move or slip past each other, which is called the deformation. Now, this deformation can be either elastic deformation or plastic deformation. As we said that elastic deformation happens when it is linear, that means the load and the extension curve is linear, and if it is non-linear, okay, beyond of course yield point, this is the plastic deformation. Now, let us see the amount of shear stress which is necessary to affect the slip, that means how much we want that shear force, so that the layers could be permanently moved or permanently slipped along the slip plane. All right. Let us say this is the black lines are the atoms which are in the initial position, and because of the shear stress which is applied, okay, to the lattice structure, to the material, let us say, that means on the lattice structure of the atom has moved from this position to this position, okay, which is x. X is the movement of the atom because of the application of the shear stress tau. Now, the distance between the two layers is b, and the distance between the two atoms, that is the interatomic distance, this is let us say a. All right. So, in that case, the within the interatomic distance, the movement of the atom, okay, that is the x, how the x moves, this can be represented by this curve, where the tau 0 is the maximum shear stress which is being applied, all right. So, that this movement takes place and then it goes like that in a sinusoidal way, all right. Now, that means once again this is a lattice structure and initially that was in the equilibrium position, all right. Then there is a shear stress which is being applied to the lattice structure, and because of that the atoms are moving from this equilibrium position to another position, and this movement is let us say x. So, within that interatomic distance, the atom will be moving like this, where tau 0, this is actually given by the maximum shear stress which is required to cause that slip. Okay, this we are causing at the slip, that means the movement of the atom from the equilibrium position, this is the x. All right. Now, we will define what should be the value of the tau 0, this is the maximum shear stress that has to be applied to affect the slip in our next session. Thank you very much.